A century underground. What remains of a human body? Prepare for a scientific look at eternal rest. When life leaves the body, an incredible, irreversible transformation begins. It's not instant dust. It's a complex sequence triggered by nature itself. And it starts even before the body enters the coffin. Immediately after the heart stops, a process called autolysis begins. It's self-digestion, where enzymes that once supported life start breaking down the body's own cells. Imagine internal builders suddenly dismantling their own structures. This starts with tissues most sensitive to oxygen deprivation, like the brain and internal organs. Simultaneously, the body cools. This is algor mortis, or post-mortem cooling. Next, bacteria move in. Our body is an ecosystem, and millions of microorganisms, especially those in the gut, start multiplying rapidly when the immune system shuts down. They access nutrients in the tissues and get to work. This is putrefaction, and it causes bloating from gas buildup and changes in skin color. These initial stages, autolysis and putrefaction, lay the foundation for everything that follows. They pave the way for further decomposition, turning a complex organic structure into simpler elements. It's just the start of the body's long journey 6 feet under. Do you know who the main architects of bodily transformation are after death? It's an unseen workforce, an army of microorganisms and insects that start this amazing, if gruesome, process. After internal enzymes and gut bacteria do their thing, a whole host of external helpers arrive on the scene. These unseen workers, microorganisms and insects, play a key role in speeding up decomposition, literally taking the body apart. Flies are often the first responders. Drawn by the smell of decay, they lay eggs that quickly hatch into larvae or maggots. These small but voracious creatures can devour significant soft tissue in a remarkably short time. Their activity is so predictable that forensic entomologists use larval development stages to estimate time of death. As soft tissues dwindle, other insect groups like carrion beetles get involved. They feed on flesh remnants, fly larvae, and other small invertebrates, acting as a sort of cleanup crew. Don't forget fungi. Though less visible than insects, they are just as important. Fungi, especially molds, start growing on the body, breaking down more resilient organic compounds that bacteria and insects might have missed. Their mycelia penetrate deep into the tissues, promoting further decay. So after death, the body becomes a temporary home and food source for an entire ecosystem. Each species performs a unique function, working together to return organic matter to the cycle of nature. This complex, multi-stage process ensures nothing goes to waste. Every element of the body is ultimately recycled and reused. No one tells you how much the final resting place, from the coffin to the soil type, affects the body's fate. It's a true underground laboratory where every factor matters. Once the body is underground, it enters an underground laboratory where every environmental factor plays a key role in decomposition. The coffin itself, its material and construction greatly affect the speed of transformation. A non-airtight wooden coffin allows air, moisture, and microorganisms to enter, accelerating decay. Airtight coffins made of metal or dense wood create anaerobic conditions, slowing decomposition and sometimes leading to saponification, grave wax formation. Soil type is another regulator. Clay soil, dense and poorly aerated, slows decomposition, promoting preservation. Sandy soil, on the other hand, provides excellent drainage and oxygen access, accelerating the process. Peat bogs, saturated with acids and lacking oxygen, can lead to natural mummification, preserving soft tissues for centuries. Humidity and temperature are major catalysts or inhibitors. In warm and humid environments, bacterial and insect activity increases dramatically, speeding up decay. Cold, conversely, slows or completely halts biological and chemical processes, preserving the body. Low humidity promotes desiccation and mummification, while high humidity with limited oxygen favors adipocere formation. Burial depth also matters. The deeper the body, the more stable the conditions, with less temperature and humidity fluctuation and limited oxygen access. All these factors, interacting in complex ways, create a unique decomposition scenario that determines what remains of a person after a century underground. Imagine an archaeologist carefully brushing away earth from an ancient burial a century later. Among the decay, they most often find them, bones and teeth. These incredibly durable witnesses of the past are the human body's last stronghold. When soft tissues finally succumb to time, the most resilient elements of the human body, bones and teeth, take center stage. This is the last fortress capable of withstanding a century underground, and they are often the main witnesses to a person's existence. Their resilience lies in their unique mineral composition. Bones consist mainly of hydroxyapatite, calcium phosphate, which gives them exceptional hardness. Organic collagen decomposes over time, but the mineral matrix remains, forming a kind of natural stone framework. Teeth are the hardest structures in the body. Their enamel is almost entirely mineral, surpassing even bone in strength. Dentin and cementum are also resistant. It's no wonder teeth often outlast the complete disintegration of the rest of the skeleton. However, this fortress is not invulnerable. The preservation of bones and teeth after 100 years depends heavily on the environment. Acidic soil, like peat bogs, can gradually dissolve the mineral base, making bones brittle or even destroying them completely. Neutral or slightly alkaline soils, on the other hand, promote better preservation. Moisture is also important. Constant exposure to water can leach minerals, while dry conditions aid in conservation. After a century, we'll most often find a complete or partial skeleton. Bones may be altered, become porous, or fragment under the influence of external factors, but their basic structure, carrying invaluable information about a person's age, sex, and diseases, remains. This allows scientists to look into the past. While most bodies decompose within decades, there are striking exceptions. In certain conditions, soft tissues can remain preserved not just for 100 years, but for millennia. For example, the age of the famous bog bodies reaches 2,000 years. Despite the general path of decomposition, there are amazing exceptions where soft tissues are preserved for decades or even centuries. These are paradoxes of natural preservation due to highly specific environmental conditions. Dry climate. In deserts or dry caves, the body quickly dehydrates. The lack of moisture halts decay, and tissues dry out, turning into parchment. This is how mummies were preserved in ancient Egypt or the Andes. Extreme cold. Permafrost or glaciers completely freeze the body. Low temperatures block biological and chemical processes, preserving organs and tissues for thousands of years, as in the case of Ötzi the Iceman. Peat bogs, a unique environment. High acidity, lack of oxygen, and tannins create ideal conditions for soft tissue preservation. Skin and hair are tanned, acquiring a dark color, while bones may dissolve. Bog bodies are a prime example. Adipocere, grave wax, in some humid, oxygen-free conditions, e.g., in clay or underwater, fatty tissues transform into a wax-like substance, adipocere. It preserves the body's contours for a long time, altering its chemical composition. These rare phenomena show how nature, under certain circumstances, can defy standard decomposition processes, leaving behind striking evidence of the past. Imagine that after a century of oblivion, a faint whisper from the past becomes audible again. This is how archaeologists and forensic scientists work when human remains, seemingly long reduced to dust, begin to reveal their incredible stories. After a century, when only bones and perhaps teeth remain, their significance for science only increases. These silent witnesses hold an incredible amount of information, capable of shedding light on long-gone events and lives. For archaeologists and forensic scientists, the skeleton becomes an invaluable source of data. From the shape of the skull, pelvis, and long bones, it's possible to accurately determine a person's sex. Analysis of teeth and bone growth zones allows estimation of age at death. Even ethnicity can be suggested by certain skeletal features. But that's just the beginning. Bones can reveal diseases suffered during life, traces of arthritis, fractures, infections that left their marks. Nutritional deficiencies or hard physical labor also leave characteristic changes. For example, patterns on vertebrae may indicate heavy work, while certain deformities indicate chronic ailments. Sometimes even the cause of death can be determined. If there are signs of violence on the bones, bullet holes, cut marks, experts can reconstruct events. In archaeology, analysis of mass graves helps understand the scale of epidemics or military conflicts. These findings are not just facts. They give us the opportunity to reconstruct the way of life of people in the past, to understand their suffering and achievements. Each bone, each tooth is a page in a history book that scientists patiently read to bring the past to life. Our deep dive into the mysteries of a body's century-long journey to oblivion has come to an end. If you're as fascinated as we are by unsolved phenomena and scientific explanations for the most intriguing mysteries, subscribe to Mysteries of the Spirit and like this video. Together, we'll continue to explore the unknown.